Welcome to this talk on Hot Swap Your Data Store, a practical approach and lessons learned. In this talk, I'll talk about a project at Quantcast where we replaced an in-house custom key value database with a commercial, more modern database without any disruption in our service. So, who we are? My name is Raj. I'm a staff system engineer at Quantcast. My co-author on this presentation is Mehmet, who is a senior software engineer at Quantcast. To set the context, a little bit about Quantcast. Quantcast is an ad tech company that started in 2006. We started with Quantcast Measure, which was used by publishers to gather analytics data about visitors to their site. And in 2009, we started online advertising as well. And in 2012, we got into real-time scoring for online advertising. One final product that we also offer is called Quantcast Choice. This is a content management platform used by publishers to comply with privacy regulations. A little bit about how real-time bidding works. So when a user loads a web page, there can be an ad opportunity on that web page. The ad opportunity is managed by an ad exchange. The ad exchange fans out this request to multiple ad providers. Quantcast is one of the ad providers, and it responds back with a bid and an ad. And if the ad exchange decides which the winning bid is, based on the whoever wins the bid in the ad exchange, the ad is shown to the user. The thing to note about this whole process is that it's pretty fast and it happens in the background, generally under 100 milliseconds. And this is a more overview of how the real-time bidding stack works in Quantcast. The ad exchange sends the ad request, and that request first comes to a system called MUX. The MUX applies some filters and removes ad opportunities that we don't want to participate in. The ad request might be fraudulent. It might be on a page that we don't want to show our ad inventory on, things like that. And it finds out the details about uh, the cookie that has come with the ad request. We use a cookie data store which we built in-house, and it's called Keebler. It stores the features of a cookie, and it responds back with those features to MUX. And these features can be things like user demographic, interest, sites that the user has visited, and marketers for which the user has seen the ad for. The MUX then sends the cookie, the features to our bidding system. The bidding system has multiple models and it computes the best ad and the best price for this ad and sends it back to the MUX, which then sends it back to the ad exchange. Hopefully, the idea is that Quantcast has done a good enough job of targeting the ad and finding the optimal price for this ad that we win the auction and the user gets to see an ad from the Quantcast inventory. So these are some numbers to give you an idea of the scale. We handle almost at our one of the biggest regions that Quantcast has handles 1.8 million requests per second at peak. Combined, all the regions handle almost 3.3 million requests per second. The big thing for us is the latency. We try to perform all the computation and lookups under 80 milliseconds. So if the request takes longer than that, the ad exchange might stop sending us ad opportunities. So The in-house key value data store that we use to store cookie data is called Keebler. We have been using it since 2010. Um, it started as a database of cookies and the information associated with the cookie. Over time, it morphed in as a storage for more and more information that we wanted to use during bidding. For example, we would use it to for frequency capping so that we don't show an ad very frequently to a user. We run a Keebler cluster in all the AWS regions that we have our bidding infrastructure in. I'll do a deep dive into what a single Keebler node looks like now. So we have a lot of data and it cannot fit on one machine. So we have it partitioned across multiple nodes. There are two parts to a cookie data. One is the immutable uh, cookie data that we store on SSD disks, and this is computed and refreshed every day. Um, the other part is the real-time updates that come in for a cookie, and this is stored in the Redis database. When a MUX client or any client which wants to use Keebler, when they make a request, the Keebler looks up the data from the SSD. It looks up the data from the Redis and merges both this to respond back uh, to respond back to give a full overview of what all the data that we have on a specific cookie. Keebler also uses memcache to reduce the amount of computation it has to do during runtime, and we have a somewhat okay hit rate for the caching that we do. So given the circumstances, like it has worked well for us since 2010. It has a good latency performance most of the time. So why are we thinking of replacing Keebler? The big thing for us was the number of machines. It takes a lot of it takes a lot of machines to run the Keebler cluster. It's a huge cost. Plus, it's also an operational uh, headache to maintain this large number of machines for each cluster. There were some operational complexity as well. If we had a if we had a bad if we had a few bad nodes, or if we had some hot nodes in the cluster, it would mean that we would have to manually go and reshard uh, and distribute the load on all remaining nodes manually, and it had unreliable performances. So we would see like tail latencies would be would the tail latencies would not be too good, especially during peak traffic. Um, I'll go into why this was the case a little further in the presentation. Since we did at peak, what we had noticed is that during peak traffic, the cache hit percentage would uh, deteriorate, and and this would lead to higher latencies from Keebler during key lookups. The other problem that we would run into quite a few times is the EBS volumes running out of IOPS credit. What this would do is that we would see the latency for some request to spike up, uh, and then and then it would recover. It would take quite a long time to recover back from running out of IOPS credit. The bad hit cache rate, uh, the IOPS credits problems, both of this would cause us uh, uh, would manifest as like bad tail latencies, especially during peak traffic. The other issue was also that we had lost the institutional knowledge that we had. Keebler was a great key value data store when it started, but over a period of time, it became hard to maintain, and it also became harder to support new product features that we wanted to ship out. Uh, and there was an indirect cost to running Keebler. We had a MapReduce job, and this would run a sort every Sunday, and we would see our compute cluster scale out at very unpredictable times and to very unpredictable costs, uh, almost every week. But it was hard to find a good solution to this cost. So we decided to replace Keebler with something better, with something which was easier to maintain. So um, and we knew the requirements quite well. The number of reads, the number of writes it should be able to sustain. The cost was a big issue for us. We did not want to have something which would balloon out of hand pretty soon. Um, we also wanted something which could support new data frameworks, which had good integration with things like Spark. Uh, and we also wanted it to have good monitoring, especially we wanted something which would integrate well with the newer monitoring systems that we have. After looking around, we decided to go with Aerospike as a replacement for Keebler. However, I should note that the techniques that I'm going to present uh, in the slides don't use any specific features of Aerospike. The process that we use to migrate from Keebler to Aerospike should be applicable to any database. So once we had decided on Aerospike, we did like a quick proof of concept for this. We set up a Aerospike cluster. We loaded it up with the data that we had, and then we tried to do like a fast read of that data, and it worked quite well. However, note that we used the synchronous blocking API call for this proof of concept, and so this was like a synthetic benchmark that we did, and it worked well. However, why this was a problem and why I have highlighted it, I'll talk about it a little further in my presentation. So once we had decided that Aerospike fit the requirements that we had, we made a few design choices. One of the important thing was that we decided to implement this new system as a library. So anyone who wanted to use Aerospike would talk to Aerospike through the library that we had designed. Um, the benefit of using this library was that there would not be like the business logic would be separate from the data. What we had seen in Keebler was that it became a mix of handling a key value database as well as uh, esoteric business logic in the same system. We do not want to repeat that mistake with Aerospike. So this helped us with that. We also decided to stay away from any cryptic representation of the cookie data and just use standard data structures for storing the key value database. So once we had we had come up with the design for this new system, uh, we uh, uh, we sat down and wrote this library, and we started on the process of moving the clients of Keebler to start using Aerospike. But before we did that, we came up with what the requirements were uh, for the migration. So these were the main migration. These were the main requirements for the migration. We wanted to be able to switch back to the legacy system at any point. So we should be able to stop using Aerospike and switch back to Keebler if there were any performance regressions. Um, we wanted the ability to run our cluster in a hybrid mode. So what it means is that the clients could connect to either Aerospike or to Keebler and get back a consistent response. Uh, we wanted to keep the cost of running these two systems in parallel down, like as small as possible. Um, Correctness of data was very important to us. We did not want to lose any of the cookie information that we had, or we did not want to have corrupted data in Aerospike. In terms of latency, we expected Aerospike to perform equally or better than Keebler. And most importantly, we did not want to have any downtime in our bidding servers. So once we came up with these requirements, uh, uh, we uh, we decided how to we decided how to go about implementing meeting this requirement. So the first part of that was that we came up with a clear go no go metrics, uh, and we came up with a gradual deployment process. So the way we have our cluster set up was that each region has 5 racks of machine, and each rack can have will have close to like 20 or 30 machines. It depends on how the auto scaling is working during that time of day. And our deployment process was that we would release to one rack at a time and compare the performance of the canary rack against the control, and make sure that the metrics that we are measuring match across all the racks. Like we don't see any regression uh, 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 in the canary rack as compared to the control racks. So these were the metrics that we came up with, that we wanted to so any deployment process should make sure that these metrics were there were no regression in any of these metrics. The first one was, of course, latency. And in latency, we wanted the latency to for the lookup from Keebler and from Aerospike to match as closely as possible. And of course, we were looking at the 99th percentile latency. We were also looking at the 99th percentile latency of the whole stack. So the idea was that we should not make our threads do more work when we switch to Aerospike. Or when we start using this new library, we should not add more compute load to the existing threads. Throughput, for us, the throughput was the number of bits processed per second. We did not want to lose the performance that we had already, and if we felt that the number of bits processed by the canary rack was lower than the other racks, then it was a regression in the system. CPU usage, and if it became too high or too low, both the cases were problematic, and the overall performance of the canary rack. And in this case, the performance was like number of bid impressions, the amount of money spent in at the auction. So uh, so once we once we had a good idea about how to measure the success of the deployment, and how to deploy our changes, we were able to meet the requirements after that. So the first one was that we wanted to switch back to Keebler at any point. Our bidding stack was completely stateless. It any cookie data that it wanted, it would fetch from the data store at runtime. So for us, a safe rollback was our best safety net. To achieve it, we used feature flags pretty extensively. We used Puppet to manage our config files, and The config options were managed where in a file the feature flags would be updated in a config file using Puppet, and this would make the rollback uh, pretty easy for us. We would disable that feature flag and then deploy this change again, restart our mux, and it would go back to using Keebler. So feature flags were made our deploy process pretty fast, and as well as the rollback was pretty fast using feature flags. Uh, we also wanted to run the system in hybrid mode. Uh, we wanted a consistent response and consistent and correct response for each cookie, no matter which data store the mux or any client connected to. So uh, for that, we kept the data across two data stores consistent. We had to maintain two data pipelines to update both the Keebler and the Aerospike system, and we had to provide on-call support for both the data stores while it was in this hybrid state. the we had this gave us quite a few benefits. First of all, it made it pretty easy for us to roll back uh, roll back in if there was any issue. Uh, it also allowed us to update each region sequentially, so we did not have to try to parallelize changes across multiple regions in one shot. This made it easier for us to reduce complexity. Uh, the other uh, the other thing that we wanted to do was to verify the correctness of data in Aerospike. So we wanted to track any bugs or if we had lost data at some point in during the migration. So Uh, what we would do is that during the initial release, we would sample 1% of the response, and for 1% of the responses, we would for 1% of the bed requests, we would read from both Keebler and Aerospike and log the response from both the systems into a log file. We would have an offline job to compare the response from both the systems, and if there was a big discrepancy in the response from Keebler and Aerospike, that was a good indication that there is a bug in somewhere in our data pipeline. Uh, we were definitely able to track down a few bugs using this process. We wanted to keep the cost of running two systems in parallel. Uh, we wanted to keep the cost down when running these two systems in parallel. We were not very successful in meeting this requirement. The technique that we used here was to kill Aerospike cluster when we didn't have a use for it. So if we're coming up on a code freeze time, or we're coming up over on a weekend, we would kill our Aerospike clusters during those times and make sure our bidding stack is reading from Keebler and not Aerospike, of course. The benefit of using this process was that we were able to test out our restore and backup process pretty well. Uh, and as we, the other thing that we did to keep the cost down was to reclaim instances from Keebler cluster. So as we shifted more and more of our traffic to Aerospike, we reduced the size of the Keebler cluster and used those instance types for other purposes. Yeah. The other requirement was that we wanted equal or better latency performance from Keebler. So the first part of doing that was to verify that we have sized our Aerospike cluster correctly. What to do that, what we did is that in our largest region, the region where we get the most amount of bid requests. We used we tested it out with non-blocking dark reads uh, from Aerospike. So the Mux client or the client would make a call to Aerospike, but they would not wait for a response back from Aerospike. So this way, Aerospike would get the full flow of the read traffic from our clusters, but at the same time not have an impact if if it failed for any reason. This way, we were able to verify that we have sized the cluster, Aerospike cluster correctly, and we would be able to handle the amount of load coming in from our clients. We track our 99 percentile latency uh, quite well. We would track it for data store lookup, and we also test made sure that the full bidding stack latency did not go up for any reason when we did a release. Uh, we had a very good set of metrics which gave us very strong indicator if there were any regressions during any of our release. And we use that dashboard extensively at each release to make sure nothing was breaking. One lesson that we learned after first few times was to always do a release of a new change at peak traffic time. So the idea for behind this was that we wanted to get to know any latency bottlenecks as soon as possible. Uh, Releasing at peak made sure that we did not have to wait like a full 24-hour cycle to find out about any bottlenecks due to caused due to a release. Uh, the final requirement that we had was that we did not want any downtime uh, in services which use the data store. This we accomplished using a three-pronged approach. The first thing was that the changes would be rolled out gradually. We would first release to one canary host, then we would release the change to a canary rack. We would monitor the performance of the canary rack and compare it with the rest of the rack. And again, since we had a good set of metrics to monitor the performance, if we saw that there was any regression, we would roll back the change. Uh, so doing this gradual release definitely helped us reduce the blast radius from any bad deployment. We kept support for our Keebler system while also providing on-call support to Aerospike. This helped us to roll back if there was any issue during the release. We could roll back and go back to reading from Keebler, a system we had a good idea which we knew works correctly, and and then go back to fixing the bugs that we found during the release. The third thing was that we had well-tested rollback runbooks. So we would use feature flags to do our deployments, but we would also test out our rollback process pretty frequently. So this gave us very good idea on how to deploy a change and, if required, roll back the change pretty fast. And this reduced the blast radius caused by any regressions or any bugs in our new release. So we were able to meet all the requirements using the techniques that I went over. Now let's go over what went well during this process. Once we were done with this migration, we were able to go from around 500 hosts to 90 Aerospike instances. This has definitely reduced our infrastructure cost. It has lowered our operational headaches. We reclaimed back instances from reducing a cluster size. We were able to allocate those instances to other jobs. We were able to stop the tail latency spikes due to IOPS slowness. those are gone now. It's a much more consistent latency uh, performance at this point. Aerospike is a more modern database system. It has more better documented APIs. This has helped us with our new product releases. Uh, uh, the new databases are better integrated with Jupyter notebooks and Spark. This has helped our data scientists to test out and release new models. And we are adding new features. We are adding new features into our Aerospike, which we call unified feature store. We were able to kill off a sort job, like the weekly compute sort job that we had. And and we don't have any spikes in our cluster size, compute cluster over the weekend. Uh, Scaling down the Keebler cluster helped us reduce our running cost as well. And what were the unpleasant surprises that we ran into? And this is where I'll talk about using synthetic benchmarks versus like real production load. During our benchmarks, we used the blocking API call, and in production we use the asynchronous non-blocking Aerospike API. This led to some hard to debug latency spikes initially, but we were able to work around those issues. Uh, but yeah, this we had our deadlines for the migration process definitely got extended because what we saw in prototype did not appear uh, in production. Uh, we had teams that had been using Keebler to store multi-region data. So there was a mixing of the business logic with just pure key value data. And there were there were a tail of use cases that we had not thought about, and we had to go back and find out what those use cases were. Either remove those use cases or retire those use cases, and that caused our deadline to go over by a big margin. Uh, Another thing that we would run into is the latency spike. When we're reducing our Keebler cluster, we came to realize that there are teams who use it for things that we had not thought of, and these teams would come back to us with reports of latency spike, and then we had to revert back our changes that we had done. So finally, what are the audience takeaways here? So the big thing to know is that it is definitely possible to replace a major component of your distributed system. Unluckily, there is no out-of-box solution. You have to be, before you start on this journey, be prepared for a cycle of deploy, find a bug, roll back, fix, deploy again. The other things would be avoid synthetic benchmarks. Just try to use production software, standard production load traffic if you can, and use that as a benchmark. Safety nets. Rollback, a reliable rollback process is a great safety net. Reduce a good deployment process where a change has a very small blast radius. That is another good safety net. Feature flags are great. It makes feature flags definitely make it faster to deploy and roll back a change. If you can support hybrid mode, and by that I mean that if you can support both the legacy system and the new system, and make sure that your client get back a consistent response from both the system, you should do that. Rollback, plan for rollbacks. Whenever if you are doing a big infrastructure change where you are stopping a process across, or like retiring a huge set of machines, have a plan on how you will resurrect those back. We had tested those out before we started the changes, and that definitely helped us reduce the downtime in many of our services. Finally, thanks for attending our talk. If you have any questions, I'm on Twitter on iLunaTech, and please check out our company engineering blog. Thanks for your time.